Today, we've got something super exciting in the space and science category. We're talking about a groundbreaking simulation by a team of astrophysicists led by Caltech. For the first time ever, they've managed to simulate the journey of primordial gas from the early universe all the way to a supermassive black hole, watching as it forms a disk that feeds the black hole. This new computer simulation is shaking up our understanding of these disks, challenging ideas astronomers have held since the 1970s, and opening doors to new discoveries about how black holes and galaxies grow and evolve. New simulations are the culmination of several years of work from two major collaborations that started at Caltech, says Phil Hopkins, professor of theoretical astrophysics. The first collaboration, called FIRE, Feedback in Realistic Environments, focused on large-scale questions about how galaxies form and what happens when galaxies collide. The other, StarForge, was designed to look at much smaller scales, like how individual stars form within gas clouds. But there was a big gap between the two, explains Hopkins. Now, for the first time, we've bridged that gap. To achieve this, researchers had to create a simulation with a resolution 1,000 times higher than the best previous simulations. As reported in the Open Journal of Astrophysics, to their surprise, the simulation that revealed magnetic fields play a much larger role in the formation and shaping of the massive material disks that spin around and feed supermassive black holes than previously thought. Our theories told us the disks should be flat like pancakes, says Hopkins. But we knew this wasn't true because astronomical observations show that disks are actually puffy, more like angel food cakes. Our simulation helped us understand that magnetic fields support the disk material, making it puffier. In the new simulation, researchers applied something they call super zoom in on a supermassive black hole, a colossal object at the heart of many galaxies, including our Milky Way. These mysterious and voracious entities have masses ranging from thousands to billions of times that of the Sun, exerting tremendous influence on anything that comes near. Astronomers have known for decades that when gas and dust are pulled into these black holes' immense gravity, they don't just get sucked in right away. Instead, the material first forms a rapidly spinning disk called an accretion disk. Just before the material falls in, it shines with incredible brightness, emitting vast amounts of energy. Nothing in the universe compares to it. But much remains unknown about how these active supermassive black holes, called quasars, and their feeding disks form and behave. Disks around supermassive black holes have been imaged before. The Event Horizon Telescope imaged disks around the black holes at the center of our galaxy in 2022 and Messier 87 in 2019. But these disks are much closer and more tame compared to the disks spinning around quasars. To visualize what's happening around these more active and distant black holes, astrophysicists turn to supercomputer simulations. They input knowledge about the physics at play in these galactic environments. Everything from the fundamental equations governing gravity to how to handle dark matter and stars, into thousands of computer processors working in parallel. This input includes many algorithms or instructions for the computers to follow to recreate complex phenomena. For instance, computers know a star forms when gas becomes dense enough, but the process isn't that simple. If you just say gravity pulls everything down, the gas forms a star, and the stars accumulate, you get everything wrong, explains Hopkins. Stars do a lot that affects their surroundings. They emit radiation that can heat or push away nearby gas. They create stellar winds, like our sun's solar wind, that can sweep up material. They explode as supernovae, sometimes ejecting material from galaxies or changing their surroundings' chemistry. So the computers must also know all the intricacies of this stellar feedback, because it regulates how many stars a galaxy can actually form. But on these larger scales, the most crucial physics and what approximations can be made differ from smaller scales. For example, on a galactic scale, the complex details of how atoms and molecules behave are essential and must be included in any simulation. However, scientists agree that when simulations focus on the area closer to a black hole, molecular chemistry can mostly be ignored because the gas there is too hot for atoms and molecules to exist. Instead, the gas exists as hot, ionized plasma. Creating a simulation that spans all relevant scales down to the level of a single accretion disk around a supermassive black hole was an enormous computational challenge. It also required a code capable of handling all the necessary physics. There were codes with the physics needed for the smaller scale part of the problem, and codes with the physics needed for the larger cosmological part of the problem, but none that included both, says Hopkins. The Caltech-led team used a code called Gizmo for both large and small-scale simulation projects. Importantly, they built the Fire project so all the physics they added could work with the Starforge project, and vice versa. We built it very modularly, so you could turn on and off the pieces of physics you wanted for a specific problem, but they were all cross-compatible, says Hopkins. This allowed the scientists in their latest work to simulate a black hole with a mass about 10 million times that of our sun, starting from the early universe. The simulation then zoomed in on that black hole as a giant stream of material was stripped from a star-forming gas cloud and began to spin around the supermassive black hole. The simulation could keep zooming in and resolve smaller and smaller areas as it followed the gas towards the black hole. Surprisingly, puffy, magnetic disks. In our simulation, we see this accretion disk forming around the black hole, says Hopkins. If we had just seen this accretion disk for the first time, we'd be very excited. But what's so surprising is that the simulated disk didn't look like we thought it would for decades. In two landmark papers from the 1970s describing the accretion disks feeding supermassive black holes, scientists hypothesized that thermal pressure played a dominant role in preventing such disks from collapsing under the enormous gravity they experience close to the black hole. They acknowledged that magnetic fields might play a small role in supporting the disks. In contrast, the new simulation found that the pressure from the magnetic fields in such disks is actually 10,000 times greater than the pressure from the gas's heat. So the disks are almost entirely controlled by magnetic fields, says Hopkins. Magnetic fields serve many functions, one of which is supporting the disks and making the material puffier. This insight changes many predictions scientists can make about such accretion disks. For example, the mass of the disks, how dense and thick they should be, how quickly matter should move through the disks and into the black hole, and even their geometry. Looking ahead, Hopkins hopes this new ability to bridge the scales for cosmological simulations will open up many new research avenues. For example, what happens in detail when two galaxies merge? What kinds of stars form in galactic regions where conditions differ from those in our sun's neighborhood? How might the first generation of stars in the universe look? There's so much to do, he says. Don't forget to subscribe and hit the notification bell. See you in the next video.